We're going to talk about resolution. This is one of the most complex issues that we have to deal with as designers, and it's one of the most important. There are many kinds of resolution that we're going to talk about, and I'm just going to briefly touch on monitor resolution. Now, we know that the more pixels that you have in your monitor, the better your display is going to be. The thing about monitor resolution, and I'm sharing this because it just makes me a little bit nuts, and it may have happened to you and you may not know why. When you are viewing something on your monitor, now I have a 2-monitor setup here in my office, and what I did was I have the image on the left is on my higher resolution monitor, and I literally just dragged the whole window, the whole Photoshop window over to my other monitor and took a screenshot. And you can see that the percentage shows on my good monitor that this image is at 66.67%, and on the other monitor it's 33.33%. Now, the relationship of this percentage number to the size of your photo is not like we expect it to be. It's not about that this is showing you 33.33% view of this picture, because the view on each monitor is exactly the same size to your eye. It's the percentage based on the resolution of the monitor. So don't get mixed up when you're looking at this saying, oh, I'm looking at this zebra at a third of the size of the original. That isn't the case. And so I just wanted to share that because it makes me a little bit nuts. Now, image resolution is the biggie. And when we're talking about resolution, what we're talking about is talking pixels, okay? How many pixels do we have and how big are they? It's that simple and that complex. It's a measurement of the detail in a bitmapped image. In other words, how many pixels do you have and how big are they? Now, raster images are resolution dependent. That means you want to have as good as you need, not more, not less, at your final print size. Now, the big thing is understanding how do we determine what that is and what we need it to be. And if it isn't what we need it to be, how do we fix it? There are two kinds of adjusting resolution. One is non-destructive and one is destructive. Clearly, the non-destructive is the one we want to use. Now, I'm going to talk in sort of some odd terms, but hopefully it'll make it a little bit easier for you to understand. When we're looking at image size in Photoshop, the size of the image, in other words, if we printed it out, how big is the piece of paper we're holding in our hand, the image itself is the container. In other words, we have a container that is 7 inches by 4.667 inches. And that container holds pixels. The size of the pixel is the resolution. Okay? And at the size pixel for 300 pixels per inch, and that's in a square. So in a square inch, you have 300 times 300, or 90,000. Okay? So you have that many pixels at that size, and here's your pixel count right up here. This tells you how many pixels fit in that container at that size. Now, over here, you can see that I changed the size of my container. Okay? I changed the size of my container, and I changed the size of my pixel. I did not change how many pixels I have. This is the same over here. So the data itself has not changed. The only thing that's changed is the size of the pixel. And when I changed the size of the pixel from 300 to 72, because the pixels got bigger, the box had to get bigger. So non-destructive means I'm not changing the information that's stored in each of those pixels. In other words, my image looks just as good or bad as both of these. They're identical. It's identical data. The size of the pixel and the size of the container is different. So if I output this image at 300 at 7 inches, it's going to look great. If I output this one, even though the data is identical to the data over here, because my picture that I'm now holding in my hand is poster, it's almost 30 inches by 19.44 inches big. The pixels are really big and you can see them, so it doesn't look as good even though the data is the same. Now this will make a lot of sense here in just a minute. Destructive resolution is where you're changing the data. Okay, you're changing that information and changing the pixel information. Okay, Photoshop is the one that will decide what kind of data it's going to be. Okay, so if we look at this same illustration with the zebra, and the resample button is the one that you click to say Photoshop change the data, resample equals change the data. Okay, I am going to change my container. I have a container and my container is 10 by 6.667 and my resolution is 300. So I know how big my pixels are in a square inch. I have 300 by 300. Okay, so that's the size of the pixel. The container is 10 by 6. And my image dimensions, when I say Photoshop resample, in other words, create new data, it went from 2114 to 3000 by 2000. So Photoshop manufactured all those extra pixels. Over here, I made the container. Here's my container, 5 by 3.33, and I made it smaller. Okay, so I'm making my container smaller, and I'm saying, okay, my container is smaller now, and I still want 300 pixels per inch. You got to figure this out for me. Now my dimensions of how many pixels I have is 1500 by 1000. So it threw away information. Notice this is half the size of this, so I have half as many pixels as I have over here. In other words, Photoshop has altered the data in the pixels, has changed the pixels themselves, not just made them bigger or smaller by literally enlarging or reducing, right, and keeping the data the same, having the box fit like we did in the non-destructive. Here, I said, okay, I want you to manufacture the data with the information you have here to fit it in the box. And this can have some horrible results that we're going to look at. Okay, so here we changed Photoshop re-change. Okay, I started with 300. I didn't change my container. Okay, but I changed my resolution. So I said, okay, container is going to, so the box is going to stay the same. And I want to change the data to be this size pixel. How many pixels are going to fit in that box? And here's my answer. Okay, so it's changing the data and the size of the pixels. Over here, got our original. What we're going to do is we're going to say, okay, what I want to do here is I'm going to resample, okay, and I want to resample the information that was 72 over here, okay. So I took this one and said, all right, now I want it to be 300 again. In other words, I want it to go back to what we had before. Okay, Photoshop, come on, help me out here. I got rid of pixels. Now I need you to give me pixels back. So make me new pixels, and make me new pixels that are going to fill this container with this size pixel. Now notice this information and this information is identical. Both of these have the same number of pixels, the same size container, and the same size pixel. The difference is this is our original image with good data, and this is information that we told Photoshop, okay, Photoshop, step 1 is our original. Step 2, throw away data and give me nice big pixels. And step 3, no, I didn't want you to do that. I want you to give me back to the pixels I had before. The pixel map, the bitmap of information for these two images is identical. The data itself is very different because we said Photoshop destructively change it and then Photoshop destructively try to fix it. Here's our original zoomed in. Looks nice and clean, okay? Here's our down sample, this one right here, 72. You can see visibly the pixels. You can see that edge. It's not clean, it's not crisp, it's big pixels. You can't have as good information with big pixels. Now, here, this is the one that's the same map as this one, but you can see the quality of the image is dramatically different. Here's what happened. Photoshop started with this is this step right here, and said, oh, I need to manufacture pixels. In fact, I have to manufacture from 504 pixels to 2100 pixels, and from 336 to 1400 pixels. I have to make this new data up, and the way I'm going to do it is I'm going to sample the pixels surrounding a pixel, and I'm going to say, okay, this pixel might be, let's, for easy reference in our heads, let's say we have a pixel that's red, okay, and next to it we have a pixel that's yellow. If we have to manufacture pixels between the red and the yellow, let's say we have to manufacture 3 extra pixels on either side of that pixel, between red and yellow, what are we going to have? Orange. It's going to be a gradation between those two values. So what happens is the detail in our image gets soft. It gets fuzzy. It gets blurry. You can see how much crisper this is than this. Now, another kind of resolution that we have to think about is line screen. And line screen refers to the way we get our halftone dot. And that's the dot, as you recall, we see when we look through a loop. And what happens is when we manufacture the dots, we're going from pixels to dots. And hopefully you recall that that process is done when we rip the file or raster image process. We're taking pixels and we're turning them into dots. And we do it based on the line screen that we're going to print. And this, when we're talking about halftone dots, okay, the line screen is a mesh. Think of it as looking out the screen of your window, and it's a mesh of how many lines in an inch, a square inch, so the lines go both vertically and horizontally. How many lines can we get in a square inch? And, oops, sorry. You'll notice that the halftone dot starts at the intersection of those lines, and that's where each dot resides. So how many dots you have depends on your line screen. Now, we talked about our screen angles, and we want to go into this a little bit more now. When we print, we want that nice rosette. In other words, we don't want it to look mishmash, we want it to look clean. And so we determined that, we being a long time ago, they determined that if you put your dots of each of your 4 colors down on a different angle and you create this nice pattern, everything looks awesome. Okay, now it was determined that you want the best that you can see where you don't have something that looks awful is to have 30 degrees difference between your screen angles. Well, clearly we don't have 4 different 30-degree shifts when we're talking about dealing with angles. So the one that we put on what we call the off angle, or one that isn't 30 degrees, is yellow, because yellow is the one we see the least. It's the lightest color, and if it has a funky pattern called a moire, we can hide it. Remember, print's an optical illusion. Now, let's look at what I'm talking about. Here you can see we've got black, cyan, magenta, and yellow. And you can see when you look at those dot patterns that the yellow is kind of a squiggly sort of thing with some snakes and stuff going on. That's because it has a moire. But we don't care because we can't see it. It still looks good over here. If our angles get mixed up, you can see what happens. Things start to move. It's kind of one of those kind of optical illusions. You see it a lot on television. Well, not a lot, but some. And if like somebody, a news anchor or somebody that's being interviewed on TV has on a suit that has stripes, or maybe stripes in a dress or in a tie or some sort of a funky pattern, and they move, it's a moire pattern that you're getting, and it all of a sudden it like comes alive and it starts undulating and it kind of makes you a little bit nauseous. Well, you don't want that in print either. Now, you notice that black wasn't on a 0 angle. Black was on a 45 angle. Now, black is your most dominant color. And you can see the difference here. This explains why. If you look at the image on the left here, you can see clearly a pattern. You've got very aligned vertical and horizontal dots. And you can pick that out, and it can be very obvious when you see that. And you don't want to see the dot pattern in a halftone image. When you print it, you don't want to see it. You want it to maintain that illusion that it looks like it's all continuous tone. Okay, we put it on a 45-degree angle because that's the one that minimizes the most of that pattern that our eye will find. Our eye tries to find patterns. Okay, and we can find this one quickly. We can't find this one as quickly. Now, what does this all have to do with our resolution? There's a formula that you want to use for determining what resolution your image needs to be for print. People have always said, oh, I need a 300, and they call it DPI, even though it's not dots, it's pixels. I need a 300 DPI image. That's going to look good. They don't even know where that number came from. Well, the number came from printers who often say, if you give me 2 times the line screen I'm going to print, then I have the resolution I need. Okay, and 2 times 150 equals 300, and 150 used to be a high-end line screen. That's where that whole myth came from. The reality is you only need a 1-to-1 ratio. Okay, if your data is good in your image, you only need to have the 1-to-1. However, if we think about our black, and our black goes on that 45-degree angle, okay, if this was our square, then we could have a 1-to-1 fit. But our square gets bigger because black, when you put it on a 45 angle and get it to fill, it's 1.42. It has to be bigger because we have to allow for that angle. So the actual official resolution at print size that you need for your image to print well is the PPI of your image needs to be 1.42 times the line screen. Where do you get the line screen information? Ask your printer. Okay, hopefully this is making some sense for you. Now, when I say at print size, what I'm talking about is when you place the image into your document and you get it to where you want it to be, this is how big I want it to be, this is how I want it to look on my page, okay, that's the print size. The shortcut for that is called effective PPI. This is a screenshot from the links panel in InDesign, and you can tell the links panel, show me my real resolution and my effective PPI resolution of my images that I've placed. And what you can see here is that several of these images, the original PPI is 72. Now, we've all been told you can't print a 72 PPI image and have it look good. But we learned if you're using non-destructive resolution, if you take that image, it might be 23 inches wide or however wide it is, and we're squishing it down and making it a smaller print size. In other words, when we look at it, we're going to make it smaller. Now, we're not changing the data. Okay, non-destructive, we're not changing the data. So when we reduce it, what we're doing is we're making the container smaller so the pixels get smaller. And the smaller the pixels get, the clearer it's going to be. The reality, the effective PPI, the print PPI of these images in this document is more than sufficient for printing at very high line screens, with the exception of this one. So effective PPI, in reality, is all we really care about. Now, there's another formula, and what this formula is talking about is viewing distance, okay? And the magic number is 3438, and if you take that number and you divide by the viewing distance in inches, it will tell you what the PPI at your final print size needs to be. Now, most of the time, we're going to be dealing with the formula that we just went over, okay? This one applies when we're talking about things like billboards, or if you're going to make a banner that's going to be seen at the outfield at the ballpark, or something that is going to be seen from a great distance, okay? If we look and we say, okay, our viewing distance, if I have to look at it close up, then I'm going to need more information. But if I'm going to look at it really, really far away, my eye can't see those pixels, and the illusion is going to be much more forgiving to tell what something is far away. So your pixels can be bigger. So this formula is the one that you want to use when you're talking about something like that. Now, we've been talking about those dots, and those dots are when we're talking about using a halftone screen, or the screen angles. There's another kind of printing that uses dots, but it's not dots on a pattern. It's called stochastic. Now, in stochastic, you have the same size dots for everything, but they're random. There is no pattern. It's just random dots. Halftone is where you have the pattern, halftone dot, right? And with the line screen. And those dots are different sizes based on the color value. In other words, if we need a light blue, we might have a 5% cyan dot. If we need it to be a dark blue, we might have a very large cyan dot, because the cyan is the same color. The shade that we see optically is designed by the larger or smaller dot. Here's another example of halftone and stochastic screening. Now, there are a lot of people that think stochastic looks a lot better than halftone. I've seen really good stochastic and I've seen really good halftone. The bottom line is the printer needs to be good at what they do. And if the printer is good at what they do, then it doesn't matter which one you're going to use. They will both look good. You will have good detail if you build your file correctly and they print it correctly. The last resolution that I want to talk about is output resolution. People talk about the DPI of their printer and the DPI of their image, and the whole thing gets all muddied up because one has nothing to do with the other. If you think about it and you say, okay, the printer that I got free when I switched my prescriptions from Walgreens to CVS, and they gave me a printer, and it says it's a 600 DPI printer resolution. Wow, that's twice as good as my image, so it's going to be great. The reality is it has nothing to do with that, okay? Printer resolution is measured in dots, and it's dots per inch. How many dots per inch, both directions, do I have to print? Now, those dots are not the same as your halftone dots. What those dots are doing are printing your halftone dots. And they're doing it based on how many little tiny dots does it take to print your halftone dot. Okay, some people call them spots. I find that incredibly confusing because nobody talks about SPI. Okay, so your printer resolution is how many little tiny dots am I using to create the halftone dot that you look at through your loop. Printer resolution is very high. Most like press printer resolutions are 2400 DPI, and that means you get 5,760,000 tiny dots possible in a square inch to create your halftone dots. They're going to be very, very crisp. We'll talk about this in class a little bit more, so bring your questions and we'll have at it. Thank you.